In this video, we are going to take a look at the work done in pumping water or some other liquid out of some type of a container. So this is continuing with the concept of work that we developed in the last section. And in that section, we developed work is a force being exerted over a distance. All right. And usually that is a variable force. So we have some type of a variable force, which is some function of x, being exerted over a distance, x or delta x. And so we create an integral of that, the integral of f of x dx. So we're building on that. What is different about these problems is how we determine that force function. And sometimes that gets a little complicated. Unless you're a physics major, I know it hurts my brain, but don't worry about it. I'm going to go through some of the development very quickly. Again, if you want more in-depth analysis, read the textbook. But I'm going to tell you just what you really need to know to get through these problems. That's my job. Okay, so a few things about setting these problems up. So, typical problem, we have a tank. All right, so I'm going to redraw this over here. We have a tank. Always draw yourself a little picture. Now, it's very helpful if you measure with x equals 0 being at the top of the tank and increasing downward to the bottom. So in other words, x is increasing going down, okay? Now, some people like to use y, and because the y-axis is vertical, you could do that. There's a number of different ways you can do this, but the simplest way is to let x equals 0 be the top of the container and increasing downwards. So in this particular case, over here, we have a tank that is 10 meters. So that means that this would be x equals 10 down here. And so we have water up to a distance of 8 feet from the bottom, which means that the top of the water is at x equals 2. All right? So the top of the water is at x equals 2. The bottom of the water is at x equals 10. The top of the tank is x equals 0. So that's what I find to be the easiest way to set these problems up. So if we want to find the work from pumping water out, then the work is really overcoming the force of gravity. And so the force of gravity and gravitational pull is what makes this just a little bit more complicated than a typical problem. So what we're going to do is we're going to take a slab of water, like we always do. In other words, we're going to partition the water in the tank into little partitions, into little sections. And so we're going to determine what the work is to lift that one tiny little slab of water out of the tank. And so as it says down here, the force required to lift the water to the top of the tank is the force required to overcome gravity. So it is equal to the weight of the water. Okay? The weight of the water is the force that is required to overcome gravity. Given that the weight density water is 9,800 or 62.44 pounds. Now this is important. I'm going to come back to this in a little bit. 9,800 newtons per meters cubed. Okay, that is what they're calling the weight density of the water. Okay, so this is actually coming from two numbers. This is coming from g, the acceleration due to gravity. Okay, g is called the acceleration due to gravity, and it is 9.8, I believe it's meters per second squared. Okay, I'm going to go unitless here. And then we have the density of water, which is 1,000. So when you take the 9.8 and you multiply it by 1,000, you get 9,800. And so that 9,800 is the weight density of the water. Now, this is in the metric system. This is going to be important to know when you're doing problems. The metric system, you use the 9.8 for your G, and you use the 1,000 for your density of water. If you're working in the U.S. standard system, in other words, American units, foot-pounds, we measure things in feet, not meters, and in pounds, not newtons. So we have 62.4 pounds per cubic feet. But let's not get too hung up on that now. I just want you to understand that it's going to be important to make the distinction between whether you're working in the metric system or in the U.S. standard units. This is where it gets just a little bit confusing, so don't worry about it too much. But what we're doing is we're developing our work function. So what we're doing here is this is the volume of the water. Okay, so you can figure out the volume of the water is pretty straightforward. It's circular, so it's going to be pi r squared h. The radius is 4, and of course h is delta x. So we end up with 16 pi delta x. The force, remember, force is what they're calculating here. And so you have the 16 pi times delta x, that's the volume right there, that's your volume. And then the 9,800, which is the weight density. So this is the weight, okay? So you're multiplying the weight times the volume to get the force, all right? Weight times volume to get the force. And again, don't get too hung up on all of this. Weight times volume, force is equal to the weight density times the volume. Well, now work, we know, work is a force exerted over a distance. And so here we're estimating the work of, we're just working with this one little slab now still, okay? What is the work being exerted, that being performed or done on lifting this slab of water to the top of the tank? Well, the force we just calculated up here, which is the weight times the volume. And then the distance, remember how we are measuring? We're measuring with x being at the top of the tank, right? So that slab is a distance x from the top of the tank. So if we have a slab that's down here, the distance from the top of the tank to that slab is a distance x. So that x, I don't know if you can see it in there, is right there. They hide it in the middle. So you have the 156,800 pi delta x. That's your force. And then you're multiplying it by x, which is right there. Whoops, sorry, that's not it. You're multiplying it by your x, which is right there, to get your work. All right. So that's the work involved in lifting this little slab of water out of the tank. And then, as we always do, we are going to lift a whole bunch of slabs because we've partitioned the water in the tank into a bunch of little slabs. So we sum up the work done by all those slabs. We get a Riemann sum. Then we let the number of slabs approach infinity. And so we get the work is the limit as n approaches infinity of the Riemann sum. Now, in this particular example in your book, they're using a specific example. They don't give you a general formula for it, but I am going to do that for you in a second. So for pumping problems, the calculations vary depending on the shape of the tank or container. And so now there's a strategy. So I'm not going to go over the strategy too quickly. I'm going to show you how I do it, which is basically using the strategy in a slightly different way. But you want to sketch a picture. That's always really important in these problems. Sketch a picture of the tank. Select an appropriate frame of reference. And by frame of reference, they mean let x equals 0 be at the top of the tank. Calculate the volume of a representative layer of water, multiply the volume by the weight density, calculate the distance, multiply the force and the distance to get an estimate. That sounds very, very complicated. So here's what you need to know. This is my own little interpretation now of how I approach these problems. So first of all, if you are working in the metric system, and you know that based on the units that they give you, okay, the metric system is here. If they give you meters, all right, you know you're in the metric system. So work is this formula. The work is G, which is acceleration due to gravity, which remember I said was 9.8 always. That's G, 9.8 meters per second squared. Density. Now the density of water is always going to be 1,000, but they may give you some other liquid where the density will be different. That's why you can't just memorize that number 9,800, because if it's not water, then you're going to be multiplying 9.8 by some other density. So G, density times the volume times the distance. Very straightforward. Now G is a constant. Density will be a constant in these problems. So constants I like to multiply together and put out in front of my integration sign. Now, what we're actually going to be integrating is the volume function times the distance function, right? So the constants you're going to be given, you just need to understand that they're constants. What we have to do in these problems, if we have to calculate the volume function and the distance function, multiply them together and integrate that. Now, on the other hand, what happens if you're working in the US standard units? In other words, your problem is given to you in terms of feet. If you see the word inches or feet or pounds, you know that you are working in the US standard system or just the US system. The only difference here is there is no G. You do not need G. Work is density times volume times distance. No G. You don't have that G in there. And then your work function as an integral is simply the density comes out in front as your constant times the volume function times the distance function. So if you just remember these two things, you can do all of these problems. What you need to know is this integral and this integral, which are identical except for G. So all you need to know, are you metric or are you US? All right, with that in mind, let's do a couple examples. Cylindrical tank, 30 feet tall and 12 feet in diameter, is filled with water. The tank has a spout 2 feet tall, which the water can be pumped out. If the water has a density of 62.4 pounds per square feet, how much work is done pumping out all the water? The first thing I look at is what are my units? My units are foot-pounds, so I am working in the US standard. So I have 62.4, which they gave to me, which means that my work function is simply the density times the volume times the distance. In other words, we're going back to this equation right here. Okay, that's going to be my integral. Okay, so that's my starting point. That's what I think of first. Then I draw myself a picture. All right, so here's the top of the tank. And I'm letting the top of the tank be x sub 0 or x equals 0. And then we got the bottom of the tank. And so the bottom of the tank is going to be at x equals 30. So this slab of water that we're moving is going to be a distance of x from the top of the tank. So in order to use this formula, work is density times volume times distance, we need to figure out those three things. So we were given density. Now again, if you're dealing with a problem that's not water, they have to give you the density. If it's water, they might expect you to know that the density of water in the US units is 62.4 pounds per square foot. So that's a given. We got that. Boom. What about the volume? Well, the volume here is going to be a circle. All right, the volume of the slab is circular, so we can use the formula pi r squared times h. And so they give us the radius. The radius is 6. Diameter is 12. Don't get the diameter and the radius mixed up. Common mistake. People use the diameter instead of cutting it in half to get the radius. So, and then the height is delta x. So here is our volume, 36 pi times delta x. And now the distance that we are pumping the water is x plus 2. Now, how did I get x plus 2? Well, we are pumping the water from down here to here, right? That's a distance of x, as I already said. But remember, we have the spout. Let me do the spout in blue. This spout goes 2 feet up above the top of the tank. There's an extra 2 feet. That's what I was putting there. So we are pumping the water from x below the surface to the surface and then up another 2 feet. So the total distance is x plus 2. And now we have all the components that we need to put together our integral. So once again, my integral, the basic form that I gave you for the integral, is the density times the integral from a to b times the volume function times the distance function dx. All right, what about the bounds? Okay, I did the bounds over here. So the bounds will always be where the liquid is. Okay, so the liquid, the tank is full. So the liquid, the water in the tank is going from x equals 0 to x equals 30. So that gives me my bounds. So now we have everything that we need to put together our integral. We have 62.4 is my density. My bounds of the integration are from 0 to 30. 36 pi times delta x, which becomes dx, is my volume. And my distance is x plus 2. Let's take anything that's not a constant and remove it, which means that 36 pi and the 62.4 can be multiplied together to give us 2246.4 pi. And that means all we have to do is integrate x plus 2. So that gives me x squared over 2 plus 2x integrated from 30 to 0 and multiplied by my constant. And that gives me is a decimal number, gives me this big number, 3,599,209.6 foot-pounds. And that is how you do a pumping problem. So they're not overly complicated. They are more complicated than the other problems that we've done in this section. But again, they're not overly complicated if you just remember a few things as I've mentioned to you. You need to know these two integrals, okay? Know those two integrals. And again, the only difference is acceleration due to gravity if it's metric. So that having been said, you know if it's in the US units, you need a density, you need a volume function, you need a distance function. Find those, and you need your bounds of integration. Find those things and you'll do just fine. Let's do another problem. Assume a tank is in the shape of an inverted cone with a height of 12 feet, base, and a radius of 4 feet. The tank is full to start, and water is pumped over the edge of the tank until the height of the water remaining is 4 feet. How much work is required to pump out the amount of water? Okay, so here's a diagram. The radius is 4. The height of the tank is 12, so here is x equals 0. All the way down to x equals 12. So again, I'm letting x equals 0 be at the top. X equals 12 is at the bottom. And so we are pumping it says we're leaving 4 feet at the bottom of the tank. So we're leaving 4 feet at the bottom of the tank, which means we're pumping from 0 to 8. That gives me my bounds of integration. We're pumping the water from x equals 0 to x equals 8. We're not pumping anymore after that. Because remember, the water's coming out from the top first and working downwards. So that's the first thing I need. I need to know my bounds of integration. I also know that I'm working in the US standard units, right? Because it says feet. I've got feet. So as soon as you see feet, you know you're in the US standard. If it says meters, you know you're in the metric system. So that means, because we are working in the US standard system, that my work is density times volume times distance. Well, we know what the density is. I need to find out what my volume function is and my distance function. Those are always going to be the two things that you're going to need to figure out. So let's find the volume function first. What we need to do is we're going to be taking a slab somewhere in here, okay? And we need to figure out the volume of that slab. So the key thing here, and so it's circular. The cross-sectional area is going to be circular, but the problem is the radius is always changing. You have a constantly changing radius. So what we need to do is we need to be able to figure out what we need to come up with a function, an algebraic expression that will give us the radius at any point in here. So in other words, in terms of x, what is the radius in terms of x? And so because we have an isosceles triangle, the easiest thing to do is to use a little bit of similar triangles. And so I do that down here. So we know that 4 is to 12 as r is to 12 minus x using similar triangles. So the 4 and the 12 come from 4 is the radius, okay, and 12 is the height. So the radius is to the height of the whole rectangle as r is to whatever this distance is going to be. And that distance right there is going to be 12 minus x, right? So 12 is all the way down at the bottom. And this distance here is x. So the distance so right here, the distance is the total distance of 12 minus that x. That's getting a little messy now. Let me get rid of some of this stuff. So let's figure out now. So this is r, and we want to figure out what this green segment is. We know that this whole distance from the top to the bottom is 12, right? And we know that this distance from here to here is x. The distance down from the top is x. So that means that, keep changing my colors, that this distance here is 12 minus the x. All right, so that takes us back to here. And so solving this for r, we get r is equal to 12 minus x over 3. Simplifying it, we get 4 minus 1/3 x. Well, that's the radius in terms of x. The volume is, of course, pi r squared h. Well, now we know what our radius is in terms of a function. It is 4 minus 1/3 x. So my volume function is pi times 4 minus 1/3 x squared delta x. And we know that the distance is going to be x. The distance down from the top is x. So we've got everything that we need. All right, we've got our bounds of integration, which was 0 to 8 again. We have our volume function and we have our distance. So we put it together in our basic integral and we get this. Okay. So we have 62.4. The bounds of integration are from 0 to 8 times my volume function times my distance function. And from there, it's just a matter of simplifying it. So you've got to square the 1 minus 1/3 x, multiply that by x, and get rid of the constant, put that out there, and just go to town on it. So here it is simplified. And then find the antiderivative, evaluate the antiderivative from 0 to 8. And here is your answer in terms of pi and as a numeric number. 10,649.6 and 33,456.7. So I really love to do a couple more of these, but I'm not. If after watching this video and going through these examples, if you're having difficulty with some of the homework problems in work, let me know. If I need to, I can always pop in another video on doing a different type of problem. All right, the last topic we're going to do in the next one is on hydrostatic pressure and force, which is hiding down here, but that deserves its own video as well. You can probably see now why I've divided 2.5 into actually 2 days worth of work. There's a 2.5 part 1 and a 2.5 part 2. It's all one section, but there's a lot of information in this section, so I've kind of broken it down and taken it. If I was teaching this in class, I would teach this over 2 separate classes. All right, see you at the next video.